Welcome, dear students, to this next lecture of Engineering Physics for Unit number 4. Recap of the previous lecture where we have studied about atomic packing fraction. It is the ratio of volume occupied by the total number of atoms per unit cell to that of total volume occupied by the unit cell. Though the volume occupied by the unit cell is A cube, but it also varies along with the atomic radius, and the total number of atoms per unit cell also varies for different cubic crystals, and therefore the atomic packing fraction varies from structure to structure. For simple cubic crystal, it comes to be 0.52. For body-centered cubic, it comes to be 0.68. And for face-centered cubic structure crystal, it comes to be 0.74. Now, in today's lecture, we are going to study about the relation between lattice constant and density, Miller indices and lattice planes. Now, to study the relation between lattice constant and density, we must know what is lattice constant and what is density. For that, consider a cubic crystal with lattice constant A, density of crystal rho. Therefore, volume of unit cell, as it is cubic in structure, it is A cube. Let the number of atoms per unit cell be small n. Atomic weight of material, capital M. Avogadro number, capital N. Suppose in m gram of material contains n atoms, that is, mass of n atoms is m gram. Therefore, mass of one atom is equal to capital M by N. And therefore, from this, mass of n molecules or n atoms, that is mass of an unit cell, is n into m by n. To continue with this, let density rho is equal to mass upon volume, that is m by v, or rho is equal to m by A cube, and therefore mass m is equal to rho A cube. From the previous slide, we know that mass small m is equal to small n into capital M by capital N is equal to rho A cube. Therefore, rho is equal to small n capital M by N A cube. That is, density is equal to number of atoms per unit cell multiplied by atomic weight upon Avogadro number into lattice constant cube. This is the relation between density and lattice constant. Next is lattice planes and Miller indices. Within a crystal lattice, it is possible to identify or find set of equally spaced, not placed but equally spaced parallel planes, and these planes are called as lattice planes. Or lattice planes are flat parallel planes separated by equal distance, or that distance we can say that it is small d. Yes, the perpendicular separation between each plane is called as small d. As shown in the figure, in a given crystal, a plane, lattice plane, can be selected in any one of the way. That is, it can be selected like this vertical lines, it can be selected as these horizontal lines, it can be selected as slanting lines. But the peculiarity of these planes is that there is a perpendicular separation between these planes, and that is small d. Now next is Miller indices. What are these Miller indices? These indices are represented as HKL, that is symbolic representation of what? For the orientation of an atomic plane in a crystal lattice. Or it is the reciprocals of fractional intercepts which the given plane makes with the crystallographic axis, that is x, y and z. How to find these Miller indices of a plane? First, check the plane. Then, the first step is to determine the intercept of the plane along each of the three crystallographic directions or axes. Then second, take the reciprocal of intercepts. Next, if these reciprocals of the intercept they are fraction, then multiply each by the denominator of the smallest fraction. It gives us the Miller indices. Then these are the few features of Miller indices. What are these features? That Miller indices, they do not define a particular single plane, but they define a set of planes. Equally spaced parallel planes, the word important, parallel planes have same index number. A plane parallel to one of the coordinate axes has an intercept of infinity. Then its index is 0. We will see few examples of Miller indices. Now see in the figure, the first figure that shows the plane with this blue color. What we are observing? That this plane, it is just showing that it is touching only x and y axis. It is not touching z axis. So, the intercepts along x axis, it is 1. Along y axis, it is 1. But as it is not touching this z axis, therefore its intercept on the z axis is infinity. Now what is next step? Yes, next step is to take the reciprocal. So 1 by 1, 1 by 1 and 1 by infinity. What the answer comes to be? 1, 1, 0. That is the Miller indices for this plane that is shown in blue color is 1, 1, 0. Are you getting it? Okay. So we will see now this next plane. See this plane where it is touching, it is just touching x-axis. It is neither touching this y-axis nor touching this z-axis. And it's shown with this pink color. Now up to this A point the length is 1. Therefore up to this point where this plane is cutting this x-axis, we can consider it as half. Therefore its intercept on the x-axis is half. On y-axis infinity, similarly on z-axis infinity. Reciprocals 1 by 1 by 2, 1 by infinity, 1 by infinity, and it reduces to 2, 0, 0, and therefore the Miller indices for this are in bracket 2, 0, 0. These are next few examples. See, this plane is shown with this triangular shape. These are the crystallographic axes x, y and z, and these are the intercepts. So intercept on the axis are 3a bar, 2b bar and 3c bar. What are the reciprocals of these numbers? 1 by 3, 1 by 2, 1 by 2. These are the fractions. So what we need to do? Multiply these fractions with the LCM of this denominator. What is the LCM of these three? 2 and 2 and 3, it is 6. So multiply this each term by 6. So 6 into 1 by 3, 2. 6 into 1 by 2, 3. 6 into 1 by 2, 3. And therefore the indices of this plane, that is Miller indices, comes to be 2, 3, 3. Yes. This is one of the example that a certain crystal has lattice parameters 4.24, 10 and 3.66 angstrom unit on x, y and z axis. Determine the Miller indices of the plane having intercepts 2.12, 10 and 1.83 on x, y and z axis. These lattice parameters are nothing but a, b and c, and these are the intercepts. Now see here, for in its solution, lattice parameters are 4.24, 10 and 3.66. Intercepts are 2.12, 10 and 1.83. That is, the intercepts, if we take the ratio, they comes to be 0.5, 1 and 0.5. Therefore, the intercepts are half, 1 and 1 by 2. What is next step? Take the reciprocal. Yes, reciprocals are 2, 1 and 2. Now, the least common denominator is 2, and therefore multiplying by LCM we get 4, 2, 2, and by writing them in parentheses we get 4, 2, 4. These are the Miller indices, or 2, 1, 2 are the Miller indices for this given plane. Thank you. Its next part we will continue in the next lecture. If you have any doubt, you can ask. Thank you.